Hi everybody. Hope everybody's having a good day today so far. Today we are going to start talking about optimization. And as you can see here, we're going to begin with unconstrained optimization. And then we'll move on, not probably today's lecture, we'll move on to constrained optimization. And so what we're going to be doing both today when we talk about unconstrained optimization, and also then when we move on to constrained optimization, is we're going to be talking about first order conditions and second order conditions having to do with first derivatives and second derivatives. And we'll be talking about necessary conditions and sufficient conditions. That is, conditions that are necessary if we have a maximum or a minimum, and conditions that are sufficient to guarantee we have a maximum or a minimum. So let's get started, and we're going to start with simply pointing out that we're going to be working throughout with functions. And so the whole idea is that we're looking for points in the domain of a function that will maximize the value of the function or minimize the value of the function. So we're going to say just let f be an arbitrary function, real valued function. So notice the target space is R. So completely talking about real valued functions when we're talking about a maximum or a minimum. And the set X here, at least to begin with, can be any kind of set. Doesn't have to be in Euclidean space, could be a finite set, could be any kind of a set. For our first definition here. So in this, and again, these definitions here that we're starting with in the first very few minutes, I'm sure are going to be familiar to everybody, but again, I want to make sure we kind of all have the same terminology, all the same notation, all on the same page. So let's start with the idea of a point in the set X, or an element, that's a maximum point or a minimum point of the function. So an element is a maximum point if it's at least as large as every other point in the set. So if every point in the set gives us a value of f that's not larger than x bar gives us, then x bar is a maximum point. And same idea for a minimum point. It's got to be the case that f of x bar gives us a value that's at least as small as everything else in the set X. Notice there's nothing here that says that the maximum or the minimum will be unique, because there could be multiple points in the set that all give us the same value of the maximum. Now, obviously, we couldn't have multiple points that give us different values for the maximum, but we could certainly have multiple maximum points, multiple points that give us the same maximum value of f. And you'll notice also I put in parentheses here that we sometimes refer to this as a global maximum or a global minimum, meaning it's a maximum among all the points in X. And of course, I could leave off the word global and that wouldn't really change anything here. But for our next definition, and for really everything that we're going to do in today's lecture, we're going to actually be in Euclidean space. I started off by saying the domain of f, the set X, doesn't have to be in Euclidean space. But for everything we're going to do today, as I said, the domain is going to be in Euclidean space. And when that's the case, we say that a point is a local maximizer of the function, or a local maximum point of the function, if there is some neighborhood of x bar on which x bar is actually a global maximizer, but only on that neighborhood. So that's really, I didn't word it that way, but that's really what this definition says here. It says we have a local maximum at x bar if there's a neighborhood of x bar, an open ball around x bar, on which x bar provides a maximum of f on that open ball. And of course, the same thing for local minimum. We have a local minimum at x bar if there's a neighborhood of x bar on which f is minimized at x bar. And then you'll note also in the definition an extra idea here that's actually useful and important, and that is we say that we have a strict local maximum or minimum if if, as it says, for some epsilon, the relevant inequality is a strict inequality. So it wouldn't have to be for every neighborhood that x bar provides a maximum in, but it's a strict local maximum if there is some neighborhood on which x bar is providing a maximum, and it's the only one in the neighborhood that provides a maximum. So, in fact, let me draw a couple of simple diagrams here just to give an idea of what's going on. And in fact, before doing that, let me put on the screen the last definition that we're going to need. And I don't think we're actually going to need any other definitions today. Everything else will be working out the implications of these definitions. So this last definition says that we call a point x bar a critical point of the function if it's the function's derivative at x bar is 0. And of course, when we're in RL and not just R for the domain, the derivative is really the gradient, the vector of partial derivatives. So we would say in the case where we're in RL for the domain, we would say that x bar is a critical point if the gradient is the 0 vector at x bar. So let me draw a little diagram just to distinguish some of the ideas here. So let's put the diagram over here, and in this diagram, the domain is going to be R. So, and it's going to be the case that we are, so L is 1, and so let's see what we have here. So let's just draw an axis on here like this, and let's draw our function like this. And so this is the graph of f. And so this point here is, and assuming that the graph then goes down the rest of the way in R, this would be a global maximum point of f. And of course, none of the other points in here are global maxima. So in this case, the global maximum is unique. I mentioned a little while ago that it wouldn't have to be unique, but here it is. So we have several local maxima. And of course, it's a trivial remark that any point in the domain that is a global maximum is also a local maximum. That's obvious. And of course, it doesn't go the other way, and we have examples of that. Let's call this x prime over here. X prime is a local maximum because I can find a neighborhood of x prime, a very small neighborhood here, where x prime is at least as large as everything in that, f is at least as large as everything in the neighborhood at x prime. And I guess that's not really a local maximum there, but certainly over here I have another local maximum. So I actually have 3 local maxima, 1 global maximum, and we have two, I'll call this x tilde, and I'll call this, let's call this x star. I have 2 local minimum values, 2 local minima of f, here and here. Neither of them is a global minimum. And indeed, and this is probably a useful point in the example too, if the graph goes on continuing in the negative direction here and continuing on forever in the negative direction here, then of course f does not have a global minimum. It has 2 local minima, no global minima. And of course, it's also possible to have a function that has no global maximum, no global minimum, and no local maximum, no local minimum. Let's just take a function that's increasing everywhere. That function has no global or local maxima or minima. So That kind of covers all the cases for all intents and purposes here. So we now have our definitions over here of the concepts that we're going to work with. And so let's get started actually developing some necessary conditions, some sufficient conditions on a function and a point x bar to guarantee that we have a maximum in the case of a sufficient conditions, and conditions that have to be true if we have a maximum. So let's do that now, but let's take these little pictures off first. Okay, let's get started with working out some of our necessary and sufficient conditions for a point to be a maximum point or a minimum point. So let's start off by saying that we're going to assume that x is an open set in RL, and that f, function defined on that open set, a real valued function, of course. Everything we'll do, as I said, is going to be real valued functions, is differentiable at some point x bar in x. And all the results that we're going to give are going to be results about what happens at x bar if it's a maximum, or if we want to guarantee it's a maximum or minimum. And of course, differentiable, as we've seen, just means that the derivative of the function exists at this point. So this is going to be assumed kind of throughout everything we do here. And so let's start off to begin with working out the first order necessary condition for x bar to be a local maximum of the function f. So theorem. X bar is a local maximum of f. Well, we should say if. If x bar is a local maximum of f, then and here I actually want to write this for RL. So then the partial of f with respect to x, with respect to the ith variable at x bar is 0, I equals 1 out to L. All L of the dimensions are variables. And notice that we could have rewritten this, or we could have written it as just the gradient of f is the 0 vector, because the gradient of f is the vector of partial derivatives, and the gradient of f evaluated at x bar is the vector of partial derivatives, each of them evaluated at x bar. So we're going to give a proof, but I'm going to start by giving a proof in the case L equals 1, so when we have a real function. So let's come over here and say, what's the proof here in the L equals 1 case? Well, the first thing to note is that in the L equals 1 case, when the domain is just one-dimensional, is just the reals, that the condition here that the derivatives be 0, well, there's only one derivative, so it's that the derivative is 0. So here what we are going to verify is that f prime at x bar is 0. Derivative is 0 at x bar. And so let's do an indirect proof by contradiction here. That'll turn out to be, I think, the most straightforward way to do it, I believe. So let's say, suppose f prime at x bar is not 0, and I'm first going to suppose that it's positive. And then we can see what happens if it's negative. Okay? If this is positive, well, what's the derivative? The derivative is the limit as delta x goes to 0 of 1 over delta x times 1 over, times x, f of x bar plus delta x minus f of x bar. And so this derivative is this limit. And so if this derivative is positive, that means this limit is a positive number. And if this limit is a positive number, after all, just this thing all the way across here is a function. 1 over delta x times this, it's a function of delta x. And so if the limit of this function is a positive number, then it has to be the case that for numbers close enough to x bar, it's a positive number. Or put another way, for delta x is close enough to 0, this is a positive number. So then it has to be the case that there exists some positive delta for which the, and let me take now the limit off, well, I'll leave that on for just a moment. So 0 less than delta x less than delta implies that this expression is positive. So let's take this limit off of here. And let's put an implication symbol in here. And that's got to be positive. So again, given that the limit of this as delta x goes to 0 is positive, then it means it's got to be the case that if we get sufficiently close, delta x gets sufficiently close to 0, this will be positive. And in fact, this is the case for delta x less than 0 too, but I'm leaving that aside for now. So certainly for the delta x's that are positive, this is so. And so if this is true for all delta x's close to 0, then that means in particular, since delta x is positive, that this is positive, and that means that f of x bar plus delta x is larger than f of x bar for all of these delta x's that are small close to 0. And if that's the case, then there is not going to be a neighborhood of x bar on which x bar maximizes f, because I can find, no matter how small I make the neighborhood around x bar, no matter how small I make delta x, I am able to find delta x's in that neighborhood that, that make f larger than at x bar. So x bar is not a maximizer, so this is a contradiction. And of course, the same is going to be true if I suppose that f prime of x is negative. And in fact, instead of writing all that out, let me just replace the appropriate parts of this proof by saying, now suppose this is negative, then there exists a delta greater than 0 such that delta x negative but bigger than minus delta implies this is positive. As I mentioned a moment ago, this whole thing has to be positive. But now delta x is negative. I'm sorry, this doesn't have to be positive. If f prime of x is negative, then this is going to have to be negative. And since delta x is itself negative, it again means that this is positive as it was before. So again, it's the case that even on the left or negative side of x bar, it is again the case that we can find delta x as close as we like to x bar that will give us a larger value of f than at x bar. So again, we have a contradiction of the fact that x bar is a local maximizer, a local maximum of f. So that completes the proof. Now let's see if we can go over and prove this for RL when L is something other than 1. And of course, the same thing we did here is kind of what we're going to do over here. So we'll say, suppose that one of the partial derivatives is positive. So suppose the partial derivative of f with respect to one of the variables is positive at x bar. Well, what's the definition of the partial derivative? It is that we can find, it's that the limit, let's write this down just like we did over here. Let's say it's that the limit, and now it's the limit as h goes to 0. You say, well, what's h? Well, this is h here, and this is f of x bar plus h times the ith unit vector here. And so this limit is the definition of the partial derivative at x bar. And if the partial derivative is positive, then this limit has to be positive, just like this limit over here had to be positive. And so that will tell us, that will give us a contradiction. So before actually going on to finish the proof, let me draw a little diagram of what's going on here, because with the h and the ei, that might not be completely obvious right up front. So let's draw a little diagram of what's going on, and let's do that over here. So here we have delta x1 and delta x2, and here we have delta x, the vector delta x is the 0 vector, which is the same as saying x equals x bar. And so here, let's say, is the unit vector, the first unit vector, and let's say here is the second unit vector. And so this would be where the vector delta x is the second unit vector. This would be where the vector delta x is the first unit vector. And when we're looking at this x bar plus h times the unit vector, that means we're looking, and maybe I'll use a different color here, this area over here and over here would be where h is positive. H times E1 would be a vector on the delta x1 axis. And over here, we would have H positive, could put us here. So H times E1 would be some vector along here. H times E2 would be a vector along here. And so what we're going to say then is that since the derivative is positive at x bar, that means the limit as h gets small. So let's look at the case where, let's assume that the derivative with respect to x2 at x bar is positive. So I is 2 here. So this says that I can, for example, take a delta over here, and any h that's in here, this is h less than delta and bigger than 0. So if this limit is positive, that says I can find a delta small enough that every h that's less than that delta puts me in here with a delta x that is in here. It's a multiple of E2 in this case, and there it's got to be the case. If this limit is positive, it's got to be the case that there exists a delta greater than 0 such that if h is between 0 and delta, then that implies that this is less than 0, greater than 0. Greater than 0. And if that's greater than 0 and h is positive, then therefore we have f of x bar plus h e I, in our little picture down here, I is 2, is greater than f of x bar. Again, that's a contradiction, because it's a contradiction because we've said that x bar is a local maximum of f. And so it can't be then that for every h smaller than delta, this is larger than this, because that means that there is no neighborhood of x bar on which the values of f are always smaller than at x bar. And so that gives us a proof just for we get a contradiction here for the situations in which any one of the partial derivatives at x bar is positive. And we can do the same thing here as we did over here by saying if the partial derivative is negative, and in fact, maybe I'll just do that here. If the partial derivative is negative, then there exists a delta such that h, whoops, there should be a 0 here. H between minus delta and 0 implies this is positive. Implies this is negative because we have this negative. So this would be negative. But of course, h is negative, so that implies this is positive, which again implies that this is larger than this. And again, we have a contradiction of the fact that x bar is a local maximum of f. So that gives us a necessary condition that has to be satisfied if x bar is a local maximum. So before moving on to a sufficient condition, let me do a little schematic down here that will maybe throw into sharper relief and clarify for us the distinction between necessary and sufficient conditions, and sort of clarify exactly what they are and why they're important. So let me write down here that what we want to know about is x bar being a local maximum. So let's say x bar is a local maximum of f, and we want to know both a necessary condition that has to be satisfied when this is true, and also a sufficient condition. So let me actually do the following. What we have just done is we've obtained a necessary condition. And what that means, it's just as the theorem says, if x bar is a local maximum, then it follows as an implication that the gradient at x bar is the zero vector, or all the partial derivatives are zero. And so I'm not going to write that here. What I'm going to write here is I'm just going to write star in parentheses. That asterisk or star is my kind of surrogate notation for whatever condition we're going to end up using or talking about. So in this theorem, that star here stands for gradient of f at x bar is the zero vector. And so if x bar is a local maximum of f, that implies this condition. So this then, it would be a necessary condition. A necessary condition for x bar to be a local maximum. Being a maximum implies x star. Now, let's see what happens with a sufficient condition. A sufficient condition would be some condition that implies x bar is a local maximum of f. So the condition is sufficient to imply or ensure that this point is a maximizer. So that we would call a sufficient condition for x bar to be a maximum. And we use both of them heavily in economics. I mean, a lot of economics really turns on or is built on necessary or sufficient conditions for something to be a maximizer or a minimizer. And of course, the reason for that is that we model decision makers most of the time in economics as maximizing or minimizing some objective function. And so an example of a necessary condition here for x bar to be a local maximum would be when we're talking about a firm maximizing profit. So if f is the profit function, then x bar is a decision or an activity that maximizes profit. That implies this, implies the derivative is zero. And in fact, of course, the derivative of the profit function is the difference between marginal revenue and marginal costs. So that's a kind of a good simple example. If x bar is, let's say, a level of output of the various goods the firm produces that maximizes its profit, then it's got to be the case that the marginal revenue minus the marginal cost for each of the goods is zero, that the marginal revenue equals marginal cost for each of its products. That would be a necessary condition. And I guess I would say that in economics, probably it's the case that necessary conditions show up and get used more often than sufficient conditions. Not that these don't. These are important for many purposes too, but it's very often the case that we assume that a decision maker is maximizing some objective function, and then we infer from that whatever the necessary conditions are that follow from that, and then those necessary conditions enable us to describe or characterize different features of the decision maker's behavior. Because if he's doing this, then he's doing whatever this is. And this would then be characteristics of the decision maker's behavior. Of course, going the other way, we do that as well, because there's often cases where we need to guarantee for ourselves that something that we're seeing is a maximizer, and sufficient condition would guarantee that. And that's what we're going to do next. We're going to develop sufficient condition to guarantee that we have a local maximizer of our function. So we'll take off everything we've got here, we'll come back and we'll develop a sufficient condition. In fact, I can see that this lecture is going on a little bit long, so I think we'll just break this off, take a break here, and then we'll come back after a little break and we'll look at sufficient conditions. Okay?